Okay, so in this video we're going to be looking at solutions, how they're made, and then also we're going to review some solution math that we did last year. Alright, so remember, a solution is a homogeneous mixture where you have a solute that's been dissolved into a solvent. So if I have KCl, if I take that solid potassium chloride, I can dissolve that into water so I can pull the ions apart. And this all of this occurs because of the fact that there's an intermolecular force between the ions and then the polar water molecules. So when you dissolve something, you have to remember this is not a chemical process, but we can actually write in a chemical equation that shows the process of dissolving a compound. So if you are to write a dissolution equation, you have to remember you're not making new substances. All you're doing is you're actually just pulling those ions apart. So when you write an equation for the process of dissolving an ionic compound, okay, you have to remember the number of ions that you start with. That needs to match the number of ions that you create. You also need to remember your states of matter, and then you need to remember that a polyatomic ion is not going to break down into its elements. So if I have sodium chloride and I dissolve it, I have solid sodium chloride and I've dissolved it into water, I'm going to create the sodium ion. Do not forget the charges here, which is now aqueous, and then the chloride ion, which is also aqueous. And there's 1 to 1 because I started with 1 for each one. Remember, this is not a chemical change. It's not a chemical change. You're just pulling the ions apart. So let's do magnesium chloride now. Okay, so it starts as a solid. So I'm going to pull it apart into the magnesium ion. Don't forget the charge. It's positive 2, and then the chloride ions. But there were 2 in this compound, so there should be 2 when I dissolve it. All right, let's do magnesium phosphate. So again, we start off in the solid state, and now I'm going to pull the ions apart. So I'm going to pull it apart into the magnesium ion. Don't forget the charge, and there's 3 of those. And then the phosphate ions. Do not try to pull the phosphorus away from the oxygen. That would be a completely chemical change if you did that. That's not what's happening here. And this is aqueous. Aqueous. So a lot of people, if they're going to write this, they forget the charges, they forget the number, or they have a polyatomic ion and they're trying to pull it apart. It's an ion, it stays as PO4. Okay. And remember, this is not a chemical change. It's just that you're pulling the ions apart from each other. That's it. All right, so we did some math with solutions last year. So we're just going to kind of review that. So what you have to remember is that if you have big M stands for moles per liter. So this is a conversion factor between moles of the solute and liters of the solution. So if we have 3 big M, that would be 3 moles is equal to 1 liter of the solution. So the question is asking how many grams of sodium chloride are needed to make 2 liters of the 3 moles per liter solution. So we are going to be using this as a conversion factor between liters and moles. So if I know I'm trying to make 2 liters and I know that there's 3 moles for every 1 liter, I can figure out how many moles of sodium chloride I need and then find the grams. So we're not starting with the molarity. Okay, the molarity is a conversion factor. So you start with the 2 liters. Okay, so now there are 3 moles for every 1 liter of solution, and then now I can go 2 grams. For every 1 mole of sodium chloride, that weighs about 58.5 grams. That's from the molar mass. So if I do that math, I'm going to get 351 grams. All right, so let's look at a different one. If you have 30 milliliters of a 1.2 moles per liter solution of magnesium chloride, how many grams of chloride ions do you need? So this one, we're going to have to look at it a little bit deeper. So remember, 1.2 big M, that is the conversion factor between moles of the solute and liters of the solution. So we're not starting with the molarity, we're going to start with the volume. This is going to be 0.03 liters because this is in liters, so I want my volume to also be in liters. And I could show that step if I wanted to. All right, so then I can go to moles. And this is moles of magnesium chloride. So there's 1.2 moles for every 1 liter of this solution. Okay, now the problem is this particular problem is specifying the chloride ions. Well, I know that if I dissolve magnesium chloride, I'm going to pull it apart into the ions. I'm going to make 1 magnesium ion and 2 chloride ions. So for every 1 mole of magnesium chloride, I have 2 moles of chloride by themselves because it's specifying just the chloride. So for every 1 of these, I make 2 of these. All right, so now let's go to grams. Chloride, not chlorine gas, Cl, weighs 35.5 grams for every 1 of these. I'm not talking about the Cl2, I'm talking about the ion, which is just 1 single chloride. Be careful. So when I do this math, I get 2.556, so about 2.6 grams. Okay, so make sure that you're paying attention to the way things are phrased, because chlorine, I-N-E, is something very different than ide. Chloride implies that it's the ion, and then chloride is just 1 of these, 1 Cl. Okay, so another kind of math that we did last year deals with dilution. So a lot of times you'll have, especially with acids, you'll have a liquid already. You don't have a solid where you're dissolving it into water. So you need to take a very concentrated acid and dilute it down typically. So the way that we do this math is we use this equation right here. It's the dilution equation. And essentially it's the original molarity multiplied by the original volume. The volume that you measure out of that substance is equal to the new molarity times the new volume that you want to get. Okay, so the initial molarity will always be the one that's higher. All right, so calculate the volume of a 3.25 molar solution of nitric acid that must be diluted with water to produce 500 mils of a 1.25 molar solution of nitric acid. Okay, so my original molarity is 3.25. My volume, well, this is the volume that I need of this solution. I don't know what that is. I'm trying to figure that out. And my new molarity will be 1.25. That volume is going to be 500 milliliters. All right, so my initial molarity will be 3.25. I'm trying to find the new volume. That's equal to 1.25 multiplied by 500. I don't need to convert it to liters here technically. And then when I solve for that volume, I will get 192.3. So what this means is that I will take 192.3 milliliters of this concentrated acid, measure that out, and then I will continue to add water until I get to the new volume of 500. Okay, so if we are diluting, the process that we will use, because I've seen them ask about this, and it's also important going forward in this class to know how to make a solution. You would usually use a volumetric pipette or serological pipette. It's a pipette that's used to draw the liquid up. So you go measure that volume of the stock solution, so whatever the concentrated solution is, and then you're going to transfer it to a volumetric flask, which looks like this. And then you're going to add DI water until you get to, there's one line. So a volumetric glassware in general has one measurement. So it doesn't measure 100, then 200, it measures just one amount. So this is a 250 milliliter flask. So there's a line right there, I can kind of see it. That's 250 mils. So it only measures the one volume, but it's very precise to get to that one particular volume. Okay, so just to clarify, so if we're making an acid, or if we're diluting down an acid, you have to actually add the acid to the water, not the other way around. So if you're taking your very concentrated acid, you put it into the flask, and then you add a little bit of water to it, you could actually end up vaporizing that water, and that could be dangerous. That's because it releases energy when they interact with each other. So you're supposed to put water into the flask initially, then add the acid, and then you add water until you get to the line. All right, so when we talk about creating solutions, there are 3 steps that actually go into making a solution, like the 3 steps at the particle level. So when we make a solution, it can be exothermic where it releases energy, or it could be endothermic. It really depends on these 3 steps. So there's a step where you have to take the solute particles and separate those. So remember, anytime you have 2 objects that are attracted to each other and you're pulling them apart, it requires energy. You have to put energy into that process. If you're putting 2 particles together that are attracted to each other, that releases energy. So the first step, you have to pull the solute particles apart. That requires energy. It's endothermic. Solvent particles also need to be pulled apart. That also takes energy. It's endothermic. When you put the solvent and the solute together, when they start interacting together and they're attracted to each other, that releases the energy. So it really depends on how much energy it took to do those first steps versus the third. So it depends on the magnitude. All right, so when we make a solution, this is called hydration. So your lattice is going to be basically attacked by the water molecules, and then the ions are going to be pulled apart, and you have to remember that the negative particle, so the negative ion, will be surrounded by the positive end of the water, so by the hydrogens. The positive ion will be surrounded by the oxygen part of the water molecules, because that's the negative part, the more electronegative atom.